All right. Okay, recording started. Right. So performance challenges, right? So this is the place for everyone to practice performance optimization and tuning. This is absolutely non-profit, nothing commercial involved. We're doing this just to practicing and learning performance tuning and low-level optimizations. Let's see. Yeah, and then so this is number 5, performance challenge number 5. So you can also find the previous challenges on my blog, which is easyperf.net. So this challenge, as well as the previous one, was organized and fully driven by Ivica. So huge thanks to Ivica again. I really appreciate all the work he have done so far. Let's see. So this challenge was about Kaldi. So this is a speech recognition framework. And actually, by the way, do we have anyone from Kaldi today?
Hi, Jan.
Oh, okay, Jan. Yeah, cool. It's good that you're here. So I hope we will have something for you today.
Yeah, I'm very curious.
Yeah, but again, right? So as I said, so this is not just to be clear. There is no affiliation between us, so it's just absolutely non-profit. Everything is like we are happy even to help. So
and I am happy whatever you do, or like whatever, there is no win or loss. Like for us, like the more interest the better, so it's already win for us.
Sure, thanks. Okay, and I think from that I may turn it to Ivica.
Okay, so it's official now. Welcome everybody to the fifth edition of the Performance Challenge. And I guess, okay, I'll just give a short interview of the Performance Challenge because some of people may not be familiar with performance challenges and what we actually do here. So Kaldi is a speech recognition library, and we try to optimize that library. Let me just open the slides. So you can I created a presentation which should allow you people to easier visualize what we were doing and what was going on. So can you enable screen sharing?
Oh, sure. Yeah. How do I do that? Do you know how do I do that?
Does anybody know how to enable on Zoom?
The easiest part would
be right.
You as a host have to do it.
If it's please try now.
Mm-hmm.
I think.
Okay. Share. Okay, let me see when you see it.
We can see.
So Kaldi challenge, what changes made to Kaldi? So Kaldi is an open source toolkit for speech recognition. So people who participated already, who took part in this challenge, they already know that. So it is very famous in the sense that a lot of people are using it. The library is open source and it's free available, but it is used in many commercial projects. So it is written in C++. Most of the users of the contributors to the library are researchers and scientists. So these are people who generally know C++, but they are not aware of the details of performance. And we set our goal is to speed up speech recognition using Kaldi. Now, about speech recognition is a smaller discipline of machine learning. And the cornerstone of machine learning and in general and speech recognition is matrix multiplication. And if you ran the profile, the application, you would have seen that the most of the time is spent in matrix multiplication. So these are matrix multiplication is enabled through OpenBLAS or some other libraries, but generally these libraries are very well optimized. They're very well optimized. Matrix multiplication is probably the #1 algorithm that the CPU vendors optimize when they deliver their libraries, and these libraries, they run at maximum floating point operation per second. Now we didn't do our optimization in that part because that doesn't make sense. It is very difficult to beat them and probably unnecessary. So those things already have peak performance. What we did was we are focused on speed improvements in Kaldi itself. When you in the task description which we gave when the challenge started, there was an explicit mention which files can be changed and which files cannot. Okay. Okay. Now, so this is the profile of the. I hope you see it because the font is a bit smaller. So if you look at it, 19 seconds, these two functions belong to Open BLAS and they're part of the matrix multiplication. You see a huge amount of time spent there. Now, Jakub can correct me if I'm wrong. What we were optimizing is these Kaldi libraries, and this is the part where they do, as part of the Kaldi, they do data wrangling or data filtering. Like they're manipulating raw data. They're just removing some noise and making data into nice patterns, so this matrix multiplication can work correctly. Am I right? Hello? No answer. So, yes?
No, I'm waiting for Jakub, or like from whom you want the answer.
From the Kaldi guy, Jakub,
Okay,
right?
I guess that's me. Yes, that's. I guess you could see it that way. It's generally something that is called Viterbi algorithm.
Sorry?
And it's called Viterbi algorithm with pruning.
Viterbi. Okay.
So it's like a dynamic programming algorithm that tries to like smooth the outputs from the kernel, from the SGMM.
Aha. So it's more related to output, not the input.
Yeah.
Oh, sorry. So my mistake. So this was not the code that was not working. Kaldi was not related to the input before matrix multiplication, but after that. Okay. Now, if you have a look at here, you see that these are two functions: process emitting and prune forwarding links. And under C, you see that there is a 1.4 seconds spent in malloc, and then you see 1.05 spent in libs malloc, and then you see 980 milliseconds spent in malloc consolidate and free. So you see that this code put a lot of pressure on the memory subsystem. So there were a lot of allocation and deallocation, and that later turned out to be the case. So in the profile runtime, apart from matrix multiplication, two functions dominate: process emitting and prune forwarding links. Now, if you look at the data cache misses, you see that both functions have a huge amount of data cache misses. So I used Intel vTune profiler to check that out, and you see that there is this metric called cycles per instruction, number of cycles for one instruction. If you're about 0.5, you're doing 5. In this case, this was 3 cycles per instruction or 3.5 cycles per instruction. So on average, these instructions were very late in the pipeline. They were getting out of the CPU very slow. So the question why, and the answer is pointer chasing. That code has huge amount of pointer referencing as part of accessing data in linked list or part of accessing data through pointers. So you have a class which has a pointer to another class, and when you're accessing data through pointer, there is a data cache miss that will happen if you're not optimized. If the memory layout is not optimized well, it will happen every time. And additionally, malloc and free also take a considerable amount of time. Okay, anybody else has something to add here? Danila, would you like to add something?
No, I totally agree with you. The problem mostly was on it was memory pressure problem and lots of calls to allocator, and that led to some optimizations from my side.
Yep. Okay, so The first function is called prune forward links. So I'm giving here just a description what it does. So there are these tokens inside class, so class token, and there are many tokens inside. And this function iterates over an array of pointers to class token. So you have a class, you have a token, you have an array of pointers. So tokens are in the memory, and they're not necessarily one after another in the memory. So each token, and this function iterates over this array of pointers to class token several times. Now each token let me do it like this. So here is the graphical representation. So here in green you have a tokens, and in yellow you have forwarding links. So each token has a forwarding link list. So this is a linked list. So the first token has a linked list which has 3 members, second token which has 5, 6 members, and the third one has a forwarding link which has 5 members. Now, each element of the linked list has also pointed to other tokens. So you see here the memory layout, how does it look like? And what does the function do? It iterates over this array, and every time it goes into element, it references a pointer, then it references the pointer again, then it needs to reference this pointer, then move to the next one, reference this pointer, move to the next one, and so on. So you see obviously what the problem is. So this is how it is visualized nicely. So the problem are data cache misses. Now, how can you fix this? So if you would put this memory, this data in the memory, the performance would be awful. So what was the way? What was the way of optimization? But okay. So each pointer that the reference ring creates a data cache miss. Now, if logically neighboring data is neighboring in memory, so you have logically neighbor. So these two, this forwarding link item and these two, they're logically neighbors because they're one after another. When you access this one, then you will after that you will access this one. But if they're neighboring in memory as well, that increases the data cache hit rate. And that is one of the reasons why people from Kaldi reported that when they use another memory allocator, for example, they used to TC malloc instead of this malloc, they see increase in speed and decrease in runtime. Now, what Danila did is he proposed a dedicated memory allocator for forwarding link and for token. So this was a good approach because it decreased memory fragmentation and increased data cache hit rate. So what happened when he implemented forwarding link with a dedicated allocated, for example, these 3 forwarding links, they became neighbors in memory, and this decreased fragmentation. One of the side effects in the long run is that the system the library didn't suffer from memory fragmentation because all of these forwarding links were destroyed together. Now about the tokens, so you have a forwarding link, forwarding list. But when you allocate from that, you get an almost perfect layout. But the tokens, you cannot get perfect layouts of tokens. So because the tokens are not linearly in memory, so it's difficult to have a good layout for that. Now, still, if you have a dedicated memory allocator for the token, that also has a benefit because the tokens are more compact in memory. This still decreases data cache miss rate, although not that significantly. It also decreases TLB cache miss rate, so it works better. That was one of the way that you can do it. Jan Eisenhower had another observation that the ordering or forwarding links is not important. So you can use vector to keep the data. So these forwarding links their ordering is not important. The output of the algorithm remains the same regardless of the ordering. So you can just, instead of using linked list, because for example, when you are filtering this linked list, you are removing some of the elements. You could have used vector and then just move the element from the back to the element you deleted. And this guarantees a very good memory layout. Okay, questions? Danila, do you have any other observations here?
No, actually, yeah, I also saw that like having memory pool allocator for forwarded links improves the performance significantly, and for tokens not that, but still improves. And I saw that, I don't know, it was like mostly L2, L3 cache, like L2, L3 cache hits for tokens, and for forwarded links, it was like mostly sequential. I also remember that some forwarded links are filtered out in some other functions, so it was not always like continuous in memory, but it was very close.
Yeah, exactly. It wasn't continuous always, but it was most of the time it was continuous. So this optimization really made sense. Now the Kaldi is a library, and libraries typically do not change the global system allocator, because libraries system allocator is another library, and they don't communicate. But if you use a dedicated memory allocator just for this data structure, you can limit the allocation problem to just one library. And since all the data, the memory allocator knows exactly the size is a compile time constant, the memory allocator can be really fast. Now this not only decreases the data cache misses, but also gets rid of this malloc and free the time spent here. Okay. Now, as far as I understand, that code had some also arithmetics in it, so it was doing some computation. But compared to the data cache misses, this computation did nothing. You could have used all possible ideas for better functions, but the performance improvement, because you were using more efficient arithmetics, were negligible, because the data cache miss rate was also was bad. Okay, so I gave here one example of the solution. So forwarding links for all tokens allocated from a huge block, possibly std vector. So this is the memory allocator for all forwarding links, but instead of having it in memory allocator, you can also use a vector. The good benefit is that the vector manages the memory allocation. So this is not the ideal solution, just one proposal. If you use like this huge vector where all forwarding links are, then it's allocation simple. There is no memory fragmentation, so on. Now each list belonging to a token has its own part in the vector. So one part of the vector belongs to this token, the other part of the vector forwarding links belong to another token, and so on. So in that case, ideally, when we are doing the processing, we are going over the forwarding links vector from left to right without skipping any elements. And this is basically you're processing an array. Array is the perfect way of processing data for the CPU. Now, the referencing tokens as part of the forwarding links next talk still poses a problem. So all the forwarding links have these pointers to another token. And here you can expect data cache miss. Now, question is, how can you do better? Can you do better? Now, the question actually you can ask it differently. And the way you should ask it is, can I first process these groups of tokens, and then process this group of tokens, and then process this group of tokens? So can I do it in a different way? So if you have a look at the loop itself, it goes to this array from 0 to n, and it goes several times. Why it goes several times? It calculates something until the result stabilizes. Now, what you want to ask is, I don't want to do processes like that. I want to process first 3 elements of the vector a few times, 2 times, and then process the next 3 elements of the vector a few times, and then process the next 3 elements of the vector a few times, and not go from 0 to n. Why? Because if we process the only 3 elements or 5 or 10 elements of the vector, that case, all this structure can actually fit one L1 or L2 cache, and this can increase performance. Now, nobody tried this solution, but it's a general question if it is a good solution and is it a smart solution. The answer to that question actually depends on the algorithm. You cannot say in advance what is the best way to do it. Unfortunately, nobody tried that. Okay, any ideas, observations, and so on? Jakub, Danila? Hello?
I wanted to say that one more, that having one memory pool allocator for both forwarded links and tokens at the same time was not beneficial at all. So
yeah, you're mixing oranges and apples. You don't do that if you want to keep the data cache hit rate low, high. Okay. Now, second function is it, just a question. Now, I'm not sure. I know Danilo understands me, but do other people understand what I'm saying? Are you following all the elements of the system? So this token array, token forwarding link, so on.
Yes, I think it's pretty clear. Thank you.
Okay, for you, Jakob, yes, but for Cliff, Dominic. Is the silence mean it's not clear, or is it clear?
Dominic just wrote into chat that he understands.
Okay, okay.
So if it's a so the suggestion was to use the array for forward links, right? So and you said the ordering is not important, right?
Yeah, yeah.
So did anyone try that?
Yeah, Jan was using vectors for forwarding links, but yeah, let's say like that. He was using vectors for forwarding links, but he didn't use one big vector for all. He had one vector for this one, and then one vector for this one, and one vector for this one. Now, what was the problem? There was a problem with that approach. So generally, it was a good approach, but there was a problem. And what was the problem? These lists were typically, most of the time, 1, 2, 3 elements. Sometimes they were large, but most of the time they were short. 1 through 3 elements. And data cache misses weren't happening when you were accessing the elements inside the vector. They were happening when you're switching between vectors. So you had one data cache miss here, and then you had one data cache miss here, and then you had this data cache miss here. Now, what Jan did, what he did do is, because he was using vector and the ordering was unimportant, he just got rid of these pointers. And pointers were 8 bytes on those architectures are 8 bytes. And this is not something that is negligible. So these 8 bytes are actually make sense to remove it. The data structure, the structure, the class that holds this data becomes smaller by maybe 20%, and this increases the data cache hit rate.
Okay, it's one more question. So so how did you find there are a lot of cache misses happening in this prune forward link function?
Yeah, you use vtune, the profiler, the CPU profiler vtune. So Danilo, what were you using?
Perfstat vtune. So
yeah. So the standard stuff we use for this low level debugging.
Right. I'm a little bit curious about this. So I'm actually looking at the metrics right now in the profile right now, and I see only 4% of the cache misses actually come from prune forward links function. I mean, this is the baseline code. Sorry.
Altogether.
Yep. Actually, so the major number of cache misses actually come from sgem in copy function.
Yeah, you're just normalized by this open plus library. So you just remove them and normalize. It becomes, I believe, proof forward links is just, 1/5 of sgem call. So it's like if we remove the matrix multiplication, so it should be around like 20% of all cache misses.
Right. So you're talking about if we like if we like don't look into the sgem. Okay. All right.
Okay. So one of the things that is important is not to look only in data caches that happen because you're traversing one data structure, but actually have a lot of data, small vectors, small linked lists, small hash maps, whatever. And then you switch between them. The switch will also cost you something. The switching between them will cost you something, because when the switch happens, that's where you have a data cache miss. So you have here 3 data cache hits, and the next one is data cache miss. Now hits goes quite fast, dum dum dum, and then here you have a slowdown. Wait. Aha, here's data. Dum 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 dum. Wait. Then again, wait. Okay. Okay. Now, the second function was called process emitting. Again, we have our tokens, and each token has a state. So state is just a number, state ID. And there is a hash mapping between token and state. So you have a state and you have a token. So state is just a number, and you can go to the hash map, take this number, and get the token. Get the token which is connected to that state. Okay, now each token has a state, but it has a list of arcs. This arc is something in the terminology of, there is a vector of these arcs. Arcs are stored in a vector, so they have data localities completely fine. However, arc vectors are typically short. So again, we had a problem. First access to arc is typically cache miss. And additionally, as part of the code, there is a lookup in a hash table based on state to find the next token. This will also be a cache miss. So let's say you have token and state, they're connected. So each state has a token, and each token has a list of arcs. Arcs are stored in a vector, that's fine. But arc vectors are short, and when you switch between different arcs, you get data cache misses. Now, what the optimization, what the people did? So people use the more efficient hash map implementation. This is what Danila did. So he found an implementation, which is, so the regular hash maps, I don't know about this one, because they were using their own, but the regular hash maps resolve collisions by allocating external memory. From the data cache point of view, this is not efficient. So he used another implementation, which is available online, and that's fine. I mean, that's a good approach. It decreases the data cache hit rate. Now, Jan had a really interesting observation. State ID goes from 0 to n. So you can get rid of the hash maps altogether and use simple vectors for lookup. Now you have a vector. The good thing is that you don't have to deal with collisions. You don't have to deal with external memory. You know that there will be no collisions, so data is quite compact in memory. But even with vector, accessing random elements of the vector creates data cache misses, and this slows down the program. Now, this is what both Jan and Danila did. Now, what they didn't try is prefetching, and there was a lot of potential for prefetching here. So what I did is I used prefetching before starting the current iteration. So we have a token that is processing arcs, and I know that the access to the first element of the arc will be a data cache miss. So I prefetch arcs for the next token. And when I did this with prefetching, the runtime fell down from 6.87 seconds to 6.38 seconds. It was a nice speed up. Now, prefetching here made a lot of sense in a lot of places, and let me explain why. So imagine something like this. You know that here, when you access here this token, you'll get the data cache miss. And when you access this token, you will get the data cache miss. And then when you access this token, you get the data cache miss. Now you can try it like this. You prefetch this token, then you move on to prefetch this token, then you move on to prefetch this token. Now you go to the beginning. Now this thing is already prefetched because you were doing something else. Then you prefetch these forwarding links, then you move on to prefetch this forwarding link, then you move on to prefetch this forwarding link. Then you start from the beginning. Okay, now you have this, you don't have to wait for it. Now you can prefetch this token, then you can move on to prefetch this token, and then you can move on to prefetch this token, and you start over. Now you have data to move to the next forwarding link item. Okay. Why is this approach interesting? Now you're doing processing, you're doing like something like a multi-threading, but it's not multi-threading because everything is run on one core. Now, if you use it like this, if you do it like this, you're actually processing several lists in parallel. Now the problem is how to do that in a code, to write code that is both efficient. uses prefetching because you don't know about the memory, but actually even this switching between different, let's say, nano threads, let's call them like that, will cost you some instructions. But nevertheless, your CPU is idle, so you better do something than wait for the data and do nothing. If you can speed it up, that will completely make sense. Now, nobody tried something like that. I wrote it down in the document that was giving a hint. Now I'm gonna elaborate something about that. Are there any questions related to the things we talked about until now?
I don't have a question. I have just a note. I tried prefetching, but probably maybe in the wrong place, so I haven't seen any speed up from that.
Yeah. So exactly. So prefetching makes sense only if you do it in the right places.
Yeah.
So let me show you. Let me show you. I think this is the one. How does it look like? The prefetching experiment I did. Okay, here is it. So we have a list of tokens, and each token has an arcs, and for each token we iterate over arcs. Okay. Now, before I start iterating over arc, so I'm currently processing the element E. This is the E. But before going over arc, what I did here is I check if the next element, so E arrow tail means next element. So I was prefetching the value. So value is the token. So I prefetched the value. I also created an instance of this arc iterator. So I created an iterator that just got destroyed after that. But before destroying it, I'll prefetch the value in the iterator. So it looks stupid. It really looks stupid. This code looks like something stupid. But this is what made the function go from 6.87 seconds to 6.38 seconds. So we were actually doing more work. The CPU was executing more instructions, but this didn't cause slowdown. It caused speed ups because of these two prefetches. Now, finding the right places to put prefetches it's complex. It's not simple, and it requires you to understand the code. Okay. Now,
I'm sorry if it's a question. So do you really need like two prefetches? Did the speed up really happened after you inserted the second prefetch as well?
Yes.
Right.
Without the second prefetch, it was faster, but not as fast.
Okay.
So it needed a second prefetch. So I'm going to try just to give an explanation about these nano threads because I think it is very interesting. So but nobody tried it. I didn't have time to try it, and the approach is really nice. So there is this talk, nano coroutines to the rescue. This thing is really implemented nicely with C++ coroutines. I don't know if you know what coroutine is, but let me explain to you what it's. So you know subroutine function is a subroutine, and coroutine is like interruptible function. You go to you enter the function, you execute a few instructions, then you leave the function, you leave the coroutine, then you enter the coroutine again, and then you continue when you left. Then you can enter several times the coroutine and then you exit. So here is an example of how nano threads work with how they're called with hash maps. Now hash maps work like this. You calculate hash for the entry X, then there is a stall because you need to wait to data you have a data cache miss, and you need to wait for the data to be brought from the memory to the CPU, and then you can access entry at location X. Then you calculate hash for entry X plus 1, then you try to access it, there is a stall, and then you can access entry X plus 1, okay? Now you have this is the problem typical of hash maps, because you have each access to the elements. If the elements are randomly in memory, so we'll create the data cache miss. Now, what is the idea? The idea is to split. So you have an array of values, and you want to check if they're in the hash maps. So if you can do it like this, you calculate the entry for X hash and prefetch. Then you access entry x minus 8. It was 8 iterations earlier. Then you calculate entry for x plus 1 hash and prefetch. Then you access entry x minus 7. Then you calculate the entry x plus 8 hash and prefetch. So there is these 3 dots. That means something happening with v time. You calculate entry for x plus 8, and then you access entry x. And when you requested prefetch for x, there was enough time for the memory subsystem to deliver data. And when you access the entry x, then you get your data back. Now in measurement, we did the speed up with this approach was about 2.5 times compared when you're accessing elements like this. And these coroutines and this general access can be applied here, because you know that when you expect data cache misses, prefetching actually makes sense. And you know here that you're in this phase when you can prefetch token 0, token 1, token 2, and then you go to token 0. Okay, it's prefetched. Now I can prefetch the related forwarding links. I can prefetch it, then move to on and so on. And this can be really nicely implemented with coroutines. So we didn't do it, and I feel bad about it. So the challenge was too difficult, according to me, and with what others said. But yeah, we learn something every time. Okay, this is end of me. Anybody else?
It's one more question. So what is the benefits of nanothreads versus prefetching?
Nanothreads use prefetching.
Right.
So in nanothreads, you use, instead of accessing an element, you call prefetch, then you leave the coroutine.
Right. So this is like essentially implicit prefetching, right? So and like as opposed to explicit prefetching, where you explicitly insert those prefetch instructions.
This is explicit prefetching. You have a built-in prefetch.
Ah, okay. So right. Okay.
Yeah. So take a look at this talk. So it's a really nice talk. The guy is really smart, and they did this as a part of algorithm that works on databases. Okay.
Okay.
Okay. That's it for me. Dennis, you take over. I don't know if anybody has any questions, comments. Jakub, Vanilla, everybody else.
Do we have the final results of how much we saved or anything like that?
So, yeah, we do. We do. I can share that. Just before doing that, let me actually ask Jan. So Jan, so what's your what's your ideas? Do you think that anything really can be applied, back to the code base? Do you find that some maybe optimizations were like not general applicable to Kaldi?
I think that like most of them definitely are worth discussing about. I have to say I'm not author of the code. Like Dan is probably the author of the code, and like his scripting language is also C++. So he would be able to discuss this with you, or like at the level of details that you might find satisfying, I guess, or acceptable. I understand the high level stuff, but maybe not that much of the insights of like this decoder. So right. Maybe like my idea or my thinking would be creating whatever you have, creating as a PR, and like we will see how it will go. Like there was one design decision in the beginning that like we are not aiming at like as best performance as possible if it should be at the cost of like understandability or readability of the code. But like a lot of these things are, it seems they are very local, and like the custom allocation stuff or the prefetching VR, those look like local changes that won't confuse, let's say, a scientist trying to parse the algorithm. So I think definitely that this we could try.
You could, to be honest, I wouldn't put these kind of changes, at least at the time being. I put it. You see, I see that you have lattice decoder, simple lattice decoder faster. You can have lattice decoder with prefetch, and just copy the code.
Also
and then,
possible.
yeah, because I'm not sure that prefetching is a topic that is generally, it doesn't work always, and in some cases it can make code slow down. About the forwarding links having their own memory pool and tokens having the memory pool, that makes completely sense, and you should definitely do it. Because in that case you are making sure that optimal, the CPU is not spending cycles. Your library will work better in the long run. So if it works for 8 hours, you don't have memory fragmentation issues. You're malloc free, and so it will work better. But the other things I talked about, especially about prefetching, is something that you should take with a grain of salt. And you also have one performance. So there was also other things. I mean, in your code, 80% of the time was spent on matrix multiplication. Even if you get completely rid of everything, so all the other processing becomes 0, you'll be faster 20%, right?
Yep. Yeah, I understand that. So luckily we are using typically the Intel library for this, or the Atlas, which is also like automatically tuned. So I would say, depending on the distribution, I guess, or from where you get like specifically the Atlas binaries. But I wouldn't expect like significant gains in general cases here.
Yep.
So one thing I'm actually, also curious about is that so this is like a top function, right? SGM and in copy. I don't know what it's doing exactly, but there are a couple of things that actually bugging me. So first is that, well, okay, so this is the really, dominating the profile, right? So and first of all, it actually comes from the Haswell. So I'm using so my chip is a Coffee Lake. So this is like a eighth generation, and Haswell is like 4 generations behind. I actually just looked at the difference. I mean, in terms of microarchitecture, there are the same number of execution units, like when it comes to executing, floating point instructions. So probably no speed up. I mean, maybe that's why, we still see Haswell here, like, but it kind of, I know, I'm a little bit suspicious that I'm running, like, the newer generation chip, and I'm still calling, like, the old routine. As I said, right, maybe it's not, that important, but just one thing to note probably. If this OpenBLAS library, and I think that it definitely has some kind of a CPU dispatch in between, then it should be maybe like, called a better version. I don't know.
Sorry, please go on.
And then the second thing is actually this is like a completely scalar code, no vectorization whatsoever, for the for the top function in the profile. Maybe that's again. Well, I understand, right? So as if it's said, so there was like a rule, right? So that we don't touch the the external library for this challenge, but maybe just for something for you to like Jan and the whole Kaldi team to look at, right? There is like a sequential, what I can see here is like, sequential memory copying, right? A scalar memory copy. That doesn't look right to me. And this, like, you see, so this function is massively unrolled. Oh, I'm sorry, function. This loop is massively unrolled. But yeah, I just,
yeah, it seems like this function is copying the matrix.
And you see it's 45% of the profile. Maybe there's something wrong. So you see that all those instructions are scalar instructions. So my chip has better like features like AVX2, for example, which can copy at least twice the throughput of or even actually 4 times the throughput, right? Than the scalar.
I can just comment on that, but with respect, like how little I know, like Atlas and the OpenBLAS, they are automatically tuned, and like that usually works that people sit and write like small fractions of codes or like kernels that are essentially specified for the given computer or CPU architecture. And then some other code that during compilation tries to combine those codes together. And I just like wonder if someone did the work and sat down and actually optimized for anything higher than Haswell. That might be the reason you see only dispatch to Haswell. I'm not sure. I really don't know.
So, but this is a part of the open blast. So
Yeah.
So you're more like a data scientist than you, Jan. I'm not sure your work is as a developer. You have an expertise in speech recognition, right?
Yeah, mostly, yeah.
Yeah, so you don't know these things about libopenblast, Intel MKL. So I know that it can use several libraries. It can use MKL, right?
Yeah, and I typically use MKL when I have the chance or when I have the guarantee that there will be Intel CPU.
And do you know the difference in speed between MKL and OpenBlast?
So like MKL in general case, well, on average, MKL is the top line, but the OpenBlast or Atlas, depending what you will be using, those are not very far ahead, and sometimes they are slightly faster.
Okay.
With respect to the newest compute architecture, I would definitely try MKL. That might yeah. I think Intel is fairly careful about optimizing these things for for whatever architecture they try to sell.
Okay.
It might be that the copy, and that might be interesting chance to optimize it, is because of the transposition. So that you take a matrix that has, well, C layout, but you essentially create Fortran layout and vice versa. And that might be what the copy so friendly does. That's what I'm thinking about. I won't be claiming it's what it's doing, but I think that's the only sane thing that that the operation might be doing.
Right. Yeah. Maybe. Yeah. I agree. Yeah. It's actually, I think. Well, sorry about that. Where it is. So it calls propagate, then add mat. No, yeah. I was actually also looking for words like transpose somewhere here that will give us a hint what is really
the transpose itself, that it's done specifically as in the SGEMM. You just set the flags correctly, and the multiplication code automatically
there was a flag
figures
for
how the matrices should be multiplicated between each other.
I see. So maybe that's why TN. What is TN? Maybe that's this TN exactly means transpose. But anyway, okay. I think we're going too deep. All right. So what? Now let me share maybe the score table, right? Okay, so we actually, we must say we don't have too much submissions. I think there were unfortunately not that many participants. I guess it was like four people in total. Oh, sorry, I didn't copy the result here. It was 3.4%. So here I'm showing actually only the results of the two submissions that really had some speed ups, and well, congratulations, Danila, you won this contest with 13% speed up. Yay! And then the second place goes to Jan Eisenhower with 3.4% speed up. I'm not showing the rest of the submissions. If you folks if those folks who submitted are interested, then definitely reach out to me, and I will share their scores. But this is so far that we have. Thanks for everyone for participating.
I would like to ask, what are the next steps with this? Should I create a, I know it's probably more a question to the Kaldi people. Should I create a pull request, maybe with some prototype, and we can agree if it makes sense and so on?
Yeah, absolutely. Definitely, we have like well done as the main author would definitely look at it, and like there is also one ex-Googler that will just keep nitpicking at details. But yeah, definitely, I think that like whatever improvement, it's very interesting because like the speech recognition, it's always compute bound, and this is great improvement.
So Danila, if you are going to do that, you can add me as a reviewer. I would like to do the review there. And yeah, that's it.
Sounds good.
Yep. I mean, if you have, I have kids and wife, and I would really enjoy doing these nano threadings, but I just don't have time. I just don't have time. If you're interested in doing that, I would like to work in cooperation with you. I'm just curious, how fast can it go? But I cannot focus like this requires like 5 days of work, and I cannot focus that large amount of time on that. But if you are willing to do it, I would like to accompany you, and I would like to see what you're doing, and I would like to measure the difference on. But it's up to you, Danila.
Okay.
That's also a good question. Like how much time, like let's say Danila or anyone else, I guess like other people from the challenge could join Danila in like trying to incorporate the ideas. Like how much time you would like to spend on it. That's something to consider.
So, okay, from my side, I mean, most code is ready. I just need, to polish it and to give it a good state. I also need to double check the licensing requirements because of my employer. And once it's ready, I mean, I'm probably okay with spending, some time on the weekend just to address the comments and
Cool.
to finally get it done. I'm also I also okay with trying the prefetching stuff, but as it's showed that prefetching might be tricky, and it maybe a separate PR or something like that. Like nano threads seem interesting. However, as I know, Kaldi is built with C++11, and we would not be able to use the coroutines that
we upgraded to 14. I'm not sure if you need 17.
No, it's not. We need 20, unfortunately.
Oh, okay.
So, and but probably we can do something with set jumps and so on. But
No, not set jumps. So you can implement coroutines. It looks a bit uglier, but you don't need the coroutines. You just need. You're simulating that you can enter exit function. You don't need jumps.
Okay. Okay. You seem okay. We can write the functions in a way that we can interchange the value,
you can
interchange the iterations. Okay.
If you because it's easier with code when you do it with code routines, you just take the code, copy it, and then you just add prefetches in right places, and it looks almost the same as original. So it doesn't.
Okay.
When you simulate coroutines, you are adding this boilerplate, which actually makes the code more difficult to maintain. For your internally, you can try the approach with without with coroutines. You should just switch to the upper standard of C++, and if you see that works, you can implement it then, because it's simpler to work with coroutines, and it's a good use case for coroutines. I don't know any other good use case for coroutines.
Okay, I got you. I don't promise actually working on this approach because it seems it needs some time and like deep dive. But if I decide to do that, I'll let you know then.
Hey, Daniel, I'm just curious. So how much time you spent on this challenge, if it's not a secret, of course?
So I actually even have my screencast and so on. I decided I probably can put it on YouTube. So in total, I spent 2 or 3 days, and they were mostly like weekends. So probably 3 days, something like that.
Oh, that's nice.
But probably, I don't know, 12.5% of this speed up, or I don't know, maybe most of the speed up came from, I don't know, first several hours. So, and I was just trying to find something else, and most of the time was spent on actually non-speeding up code, but like very, very, very few percent.
Cool. That's great. Good. Congratulations. That's a good result.
Thank you.
And I hope that the speed up will also apply to other workloads in Kaldi, right?
Yeah, so actually I decided also to look a little bit broader on the picture. The picture I saw, there were quite substantial small allocation patterns in other pieces of code. And I believe the most reasonable way would be just to implement, some memory pool allocator in core utils of Kaldi, and then it can be used in places where, small allocations happen. So probably code is pre-C++ 11. That's why it has like raw use here and there. And maybe, so that was my understanding, but I dumped all GDB. I ran into GDB. I decided to have breakpoints on U with size less or equal 32, and there were, I don't know, like millions of allocations per minute, so of that size. So I'm definitely advised to work towards memory more, because yeah, you cannot use your own you cannot make people use the different allocator because it's a library, but we can work with something internal like memory pool.
Okay.
Also,
all right,
one
folks.
more thing. Yeah.
Yeah. Okay. Sure. Go ahead. Yeah.
Kaldi library is built with very conservative compiler options. For example, it does not include any SE3, and for example, it may benefit in some flat hash tables. I'm not sure that, I don't know, we should do that. But on the other hand, we have OpenBLAS, which and if it's pre-Haswell, then it probably is very, very slow. So I'm just wondering if they can bump the instruction set, if they can do it, but I totally understand if not, if the user base is so broad that we cannot guarantee any hardware.
I can give you an answer to that. So as far as the OpenBLAS or other libraries, they're built with different options, and they are mostly, even some parts of it are written in assembly. So in assembly, they're not written in. So the compiler options don't make any sense. This is a heavily memory bound core. AVX2 doesn't matter, doesn't help. Vectorization happens rarely. So the compiler rarely vectorizes, and most of the code is memory bound. You cannot do anything against it.
Yeah, okay.
So in light of changing compiler option, you can try it. I mean, they're compiling with O1, you can try with O3. They're compiling Kaldi O1 with O1, you try with O3, but I don't think the difference in speed is that big. Simply because the data cache misses are the problem, not the...
Probably. Yep. I agree.
Mm-hmm.
Yeah, I think I can confirm that. Plus, like once we enabled more aggressive optimization, especially like a few years ago, we started to run into like weird compiler bugs. At least at that time, maybe like the open compilers are much more stable nowadays. But at those times, it sometimes was fairly difficult to like debug those issues, especially when discussing over like the mailing list with people who are not very technical.
Yeah, I know, assure you that now it's much better. So for example, I know Clang is built ahead. It's tested for all Google like once in 2 weeks, and we have, I don't know, hundreds of millions lines of code with -3.
That's amazing.
Okay. Anybody else?
Any last minute questions, thoughts, notes? If anyone has any idea for a next performance challenge, if you have a good suggestion of what might be a good candidate for a performance challenge, then definitely reach out to me or Ivica. We will glad to have your suggestions and your contributions and help as well.
So the challenge was too difficult. We can agree on that, right, Dennis?
Yep.
Yeah. So next challenge should be easier. I mean, so that more people can participate. They then don't have to. The Kaldi took a lot of time to compile any change, so it wasn't practical because people are doing this as a hobby project, not as a full-time work. So if they were working for 2 weeks, 80 hours, then it would make probably the results would be quite different.
Yep. So I think the main thing that we should improve in the next challenge is that we should not require so extensive domain knowledge to being able to really do performance work. So for the challenge, it's not I think it's not the it shouldn't be a requirement, right? So that you shouldn't be an expert in speech recognition in this in the code in order to improve its performance. So I think that's the requirement for the challenge.
This wasn't like that. So I guess this code, I guess from the aspect of Yuyan, and from the aspect of the data processing, you were doing the best job you could. So this was, you tried several algorithms, and this one turns out to be the fastest, right?
Yeah, pretty much.
Yeah. So they tried several algorithms, and but algorithmically, they have reached their maximum as far as the algorithm is concerned. Now they have several implementations of these decoders. One of them is like fastest and they are using it. Maybe the other one was slow because there was some underlying hardware issues. Maybe the other one could have been made faster with this knowledge we have now. But they are using that one, and we optimize that one. And I don't think, as far as with their knowledge, they reach their maximum. Now they can, if they want to move forward, they need help from the hardware people, like software hardware people. That's us, to help them move the line further, so they can use the maximum hardware resources available. Okay. So just I want to say is that algorithmically they are fine, and everything else comes from better using hardware.
Yep. That's fair, I guess.
All right, guys. Thanks everyone for participating. I think we can wrap this meeting, right?
Thank you very much.
Thank you. Have a good rest of the day.
Bye.
Yeah. Bye-bye.
Bye.
Thank you. Bye.